we discussed about two electrolytic methods. One is called electrolysis of acetate, sodium acetate, and one is decomposition of or decarboxylation of again sodium acetate in the presence of soda lime and heat it. In that case we got carbon, hydrocarbon with one carbon atom less than the original starting material. Other was Watt's reaction. Then we discussed about alkyl halide in the presence of zinc and hydrogen. And first was hydrogenation of unsaturated hydrocarbons or alkene. Now, among the physical properties of alkane, first is the non-polar character of alkanes. The reason is, let's try to understand. The original electron of carbon is 2.55 and of hydrogen is 2.2, which is fairly close to each other, but still carbon is still little more electronegatory than hydrogen. So what happens? The covalent nature of carbon-carbon and carbon-hydrogen bonds, and due to very little difference in electronegativities between carbon and hydrogen atoms, we still have little bit of that polarity towards carbon atoms. You see here, everything is polarizing towards carbon atoms, but carbon-carbon bond are totally non-polar because they are of same electronegation. So in that case, there is no particular direction of dipole possible because there are so many CH bonds. They are non-directional and randomly placed. That leads to, first, there is a very little electronegativity difference. Next, it is non-directional. It results in formation of non-polar hydrocarbons, alkane. The alkanes are non-polar. But there do exist a force between these hydrocarbon molecules. The force is called van der Waal force. Van der Waal force is an attractive force that acts between hydrocarbon molecules, but it's a weak force. It acts only when these molecules are almost in contact with each other. That means there should be contact between surface to surface contact between the molecules. So larger is the surface area, stronger will be the force between the molecules. All surface area will increase when the length of chain increases. It means larger is the length of chain of hydrocarbon, stronger will be the van der Waal force of attraction between them that holds them together. Higher will be the such forces, higher will be the boiling point of such hydrocarbon. Longer is the chain, it means higher will be the boiling point according to van der Waal forces. Let's take an example. Ethane got melting point of 90.5 Kelvin. It's a Kelvin scale, and 111 is a boiling point. Ethane gets a bit more, 101 and 184 is a boiling point. Propane still 85 and liquid is 230.9. Butane 272, close to 0 degrees Celsius. It will be boiling point. But if you see a 2-methyl propane, both are having the same molecule weight, but it is an isomer or a branched compound of butane, which its boiling point is low. General tendency we see is as the molecular weight increases, melting and boiling point goes up. But here we saw for the same molecular weight compound, the branching results in lower boiling points because branching will make the structure more or less spherical in shape and it weakens the forces, van der Waals forces of attraction. Same goes to the other compounds. Now let's talk about conformational. Conformation is spatial arrangement of atoms or a group of atoms that can be converted into one another with rotation around carbon-carbon single bond. That's what it is. It's a rotation around carbon-carbon single bond. Although there are many different configurations are possible, but two most important conformers that are possible are eclipsed conformation. Eclipsed conformation happens when we are taking here the case of ethane, when in ethane molecule, two hydrogen atoms, the two hydrogen atoms attached to the two carbon atoms are directly over each other. You see here, we rotate it, it comes directly over each other in top view, and this stable state is most unstable state or least stable state. Other configuration possible is staggered conformation, which means the hydrogen atoms attached to the two carbon atoms are at further possible position. These conformations can be depicted using Newman projection. What is a Newman projection? One carbon atom is represented by a ring, other is with this triangular structure. This central point is carbon atom, and when we rotate, and this is an eclipsed conformation, angle of rotation is given by this difference between the two hydrogen atoms. This is eclipsed state in which both hydrogen atoms attached to two different carbon atoms are directly over each other, but here we have shown it a bit out just to represent it, otherwise they are directly over each other in eclipse conformation. In staggered conformation, they are in a furthest possible state, like here we have shown. It is here, it is in the furthest possible position. And in case of multiple carbon atom molecules, what we will do, here it is C1, it is C2. Whichever the bond we want to rotate, that will pick it up. Rest of the molecules or carbon atom we place here. For example, let's say this is a butane and I want to rotate C2 and C3 bond. So I make this is C2, circle is C3, right? And I put a 1 methyl group here and 1 methyl group here. Then which means these are two. This is a rotation of C2 C3 bond, and rest of the molecules, rest of the atoms, carbon atoms are placed in these three positions as carbon is tetrahedral And remember, this angle of rotation is called a dihedral angle. This is dihedral angle. The angle between the two different hydrogen atoms in the Newman projection is called dihedral angle. Another projection is called Seahorse projections. In the sawhorse projections, same thing, just like our Newman projection. The hydrogen atoms are placed on the same side in case of eclipsed and staggered conformation. They are having a dihedral angle when they are placed on the opposite sides. Here you see this is directly above and this is directly below. That is staggered state. Now, another is it possible to isolate the two conformers for ethane? The answer is, it's not possible. The reason is, because the energy difference between the two conformational states is so low that even at a room temperature, energy is available for the seamless conversion of staggered state into the eclipsed state and from eclipsed to staggered state. So it's not possible to isolate these two conformers at room temperature, but definitely we can isolate them by cooling them to very low energy states.